My name is Hamid, so you can just separate my name in two different names, Hamid and Reza in polynomial time. And then this is a joint work with my PhD advisor, Dr. Asbi Kanen at Oklahoma State University. And then today I'm going to talk about the optimal design of low latency virtual backbones. And please feel free to unmute yourself and ask your question if you have any question during my presentation. So yeah, my presentation will have 4 sections. First of all, I will go through some the application of it, the application of and the definition of the virtual backbones. Then I will talk about the problem. So first of all, suppose that we have a wireless network like this, and then each sensor in this wireless network has a signal range that kind of shows the range of the or the strength of that sensor. And then if two sensors have, if the range of these two sensors actually intersects each other, then they can send signals to each other directly, okay? For example, here, look at this red node and this green node. You can see that the disks around them intersect. So you can add an edge between them, and it means that you can send a message from a sensor to another one directly. So, but if the disks actually do not intersect, then we cannot send a message. For example, this green one and this red one, the disk around them do not intersect. So if you want to send a message from this green node to this red node, then you need to use some relays in between or as the intermediate nodes or sensors to send the message, okay? So, and then if you want to think about these kind of relays or actually these sensors that kind of take care about the sending messages and just passing the message, then we can talk about the virtual backbones that are represented here in green vertices here. I mean, every node in the graph can actually use these green vertices to send message to other vertices in the graph. For example, if you want to send a message from here to here, then you can just send it here to these relays, and through these relays, you can actually send your message. So this virtual backbone actually has a definition in graph theory that we call it connected dominating set. And then a connected dominating set is actually defined as follow. So a D or a subset of vertices, for example, the green vertices is called the connected dominating set here, or a virtual backbone. If you consider any vertex in the graph either belongs to this green set or is a neighbor of that, okay? So then this defines the dominating set property of this set. And then it is connected because, sorry, I see some messages or chats. Let me check. Okay, please let me know if there is something in the chat because I cannot see the chat. And then we say that these nodes actually form a connected dominating set if they actually induce a connected subgraph in the graph. So these green vertices induce a connected subgraph. And then if you look at any other vertices, it is actually neighbor to these green sets, which is called a connected dominating set. And then for applications, we can think about the different military applications in battlefield surveillance, and then we can think about the environmental or air sensing for detecting forests or landslides or air pollution. There's also a nice application in warehousing. Suppose that you have like this grid graph that is, you have this grid that kind of, and then you actually want to design the corridors such that you want to have a direct access to every item in the warehouse, okay? So then you can come up with this solution here. As you can see, the white boxes here form a connected dominating set. And then if you consider the gray blocks as the items, then you can always have direct access to these items without moving any other item in the warehouse. So with this application of the connected dominating set, we are going to talk about the latency and the importance of latency in connected dominating sets. So suppose that you have a green connected dominating set here, as you can see, this green set. And then suppose that you want to send a message from this point to this point here. So how many hops should the message take to reach the destination? So you will see if you want to send a message, then you should use these relays. Okay, so you cannot send message to non-relays things or sensors. So you will see that you need to take 8 steps here. 1, 2, 3, 4, 5, 6, 7, 8. So you need to like take 8 steps or 8 hops to reach the destination. So that is why we introduce a parameter latency S, and maybe these 8 might be too much. Maybe 8 hops might be too much. For example, in the fire sensing application that we said, if for example firing happens here, then after 8 hops, if we want to get message here, it might be too late. So that is why we want to actually bound this latency parameter and say that, hey, we want some connected dominating sets with latency at most S. Okay, so some latency and of at most S, I mean, we want to have that the maximum number of length, the maximum length of communication is actually, we want to impose that the maximum length of communication is at most S. Okay, so this is what we want. So a connected dominating set like this, for example, here might not be desirable. So with this kind of motivation, we want to talk about provide a rigorous definition of the latency as connected dominating set. We say that a subset of vertices is a latency as CDS for graph G. If you consider any node, any pair of nodes in the graph, the length of the path between nodes A and B is at most S. And then all the interior nodes that are used for example, that are used for actually going from node A to node B or vice versa should also belong to the set D or dominating set, connected dominating set that we mentioned. For example, if you look at the left-hand side here, in this picture, you can see that you can send a message from 8 to 3 in 2 hops via this node 6 or node 2, okay? So you can send the message in just 2 hops. And then the right-hand side figure is like a latency 3 CDS. And then you can see that you can send a message from 8 to 4 in 3 hops. I mean, at most, here exactly 3 hops. You can send message to 2, and then 1, and then 4. So this is actually a definition of the definition of the latency as CDS that we provide here. So before going to talk about our formulation, we also want to talk about length as vertex cut. We all know what vertex cut is. Okay, so a vertex cut is a subset of vertices that if you remove the vertices, the diameter will go to infinity. Okay, or n-1. It would be very large. And I mean n. I mean the graph will be like this. Will be go to like we have some components of the graph, and then it wouldn't be like a one component graph anymore. So, but we generalize that definition and we provide the length as vertex cut of G, and we say that a subset of vertices is a length as vertex cut. If you remove those vertices and calculate the diameter of the graph, the diameter exceeds a number S here. And then you know the diameter of a graph. The diameter of the graph is the maximum, the maximum length of all shortest paths in the graph. Okay, so if you calculate the shortest path between any nodes in the graph, any pair of nodes in the graph, and then take the max, then that's the definition of the diameter. So then in this graph, you can see that the red node form actually a length 7 vertex cut. Why? Because if I remove these 2 nodes, then there exists a pair of vertices for which the distance exceeds 7. Okay, so if I remove these 2 red nodes, then the distance from this node to this node would exceed 7. So how it is like, if you remove these 2 nodes, then you should take at least 7 hops to reach the destination here. So it would be 1, 2, 3, 4, 5, 6, 7, 8. So you see that the distance between a pair of vertices actually here exceed to 8. So with this definition, we want to actually provide a relationship between the latency SCDS and the length S vertex cut. Okay, so the proposition that we define, we say that these two definitions these two arguments that we provide here are actually equivalent. I mean that if you have a dominating set, a latency as connected dominating set, then for every length S vertex cut in the graph, the cardinality of the intersection of D and C is at least 1, okay? And vice versa, okay? If for every length S vertex cuts C you have this relation, then D is actually a latency as CDS. And then with this knowledge and the relationship between these two, we propose a formulation, an IP formulation, integer programming formulation, in which we have xi's that says xi is 1 if vertex I is chosen in the latency S connected dominating set, and 0 otherwise. And then based on the definition that, based on the proposition that we provide here, the relationship between these two, we can actually add our constraint and introduce our constraints and say for every length S vertex cut C, we have the summation of xi is at least 1. And actually, the previous proposition actually proved the correctness of our formulation here. And in this formulation, the number of variables is good. We have order of n variables, but the number of constants is exponential. Okay, so now we should think about how can we add these constraints, because if you want to introduce them upfront, then maybe you go out of stock and you cannot run your model on the solver. So what we actually do, we start with some initial cuts. Okay, so you can think about every vertex and look at the neighbors around that. And then if you look at the vertex and remove the neighbors around that, those neighbors actually form a cut, vertex cut. And each vertex cut is actually a lengthless vertex cut. So you can actually start your formulation, start this formulation with those neighboring cuts, okay? So we can say that for each node, we consider cuts, the neighbors as the cut, and then add n constraints upfront with order of m non-zeros, but m is actually the number of edges. And you can start with that. But after solving the problem with initial constraints at a branch and bound node, you get a solution like x star. And then you should look at this solution and check the feasibility. If your solution is feasible or not, or does it actually satisfy all the constraints here? So this problem is actually the separation problem. And thanks to the nice theorem of optimization equal to separation, we can say that if we can solve the separation in polynomial time, then we can solve the LP in poly time. So the problem here, the separation problem, is that we have an x star, and then we want to check if there is a length S vertex cut such that the summation of xi star is less than 1. And then we found that we can find this length S vertex cut in poly time when S is at most 4, but finding such a C is hard when S is at least 5. And then in all these cases, I considered xi as a fractional point. Okay, so I mean, the fractional separation is easy when S is less than or equal to 5, and then it is hard when S is greater than or equal to 5. Okay, sorry, I mean easy for S less than or equal to 4 and hard for S greater than or equal to 5. So then, as I mentioned, we initialize our formulation with some constants like this. We start for every vertex. We say that the neighbors of that form are cut, and we start with this formulation. And then we add these constants on the fly. The point that is that we separate the integral points in poly time, okay, regardless of what S is. So I mean, in the branch and bound nodes, we actually find the C just for the integer points. And here is some of our results about how latency as CDS is. So for some instances, like These are like artificial instances that you can see with, for example, here the number of vertices is 30, this is the density, and then here are our real world instances that we have. For some instances, you can see that if we consider a very strict case of S, which is diameter of the graph, the objective doesn't change when we compare it with just the connected dominating set, okay? But for some cases, the difference is a lot. I mean, for example, for this case, RTS 37, 34, or I mean, we will see it's like if it is a lot or not, but 3, here the difference is 3, difference is 3 here, but in some cases they are the same. So for some instances, it doesn't cost, but in some cases, yes, it costs. So, and then we kind of propose a Polysized formulation, which is like, we inspired this formulation from a nice paper of Dr. Vermayev and Bujinsky. There's a nice paper, an e-journal nice paper in 2012. And then you can see like these kind of formulations for like other problems like S-clubs and S-club partitioning problems. You can also see the same idea there. So inspired by this, we proposed a Polysized formulation, and then we kind of compared our length-bounded cut formulation with the Polysized. So although the Polysized formulation is compact and the number of constants is bounded, but the LBC or length-bounded cut is actually work good here if you compare the times, and because of thanks to the lazy callback or cuts that we add on the fly. And then the other important thing in our implementation is minimalization of our constant. When I say minimalization, I mean that you can add, yes, you can find cuts and add these cuts, but you should think about like minimalizing this C and make the right-hand side as small, as minimal as possible, okay? So that is why we also propose some algorithm to minimize this set C to make our formulation strong. Otherwise, you can see that actually without minimalizing, we cannot solve many of these instances in a time limit of 1 hour, okay? So I'm talking about the 1 hour time limit. So then we can think about the robust case of the latency SCDS. There are some cases that if one of these relays or the vertices in the latency SCDS actually fails, for example, here, you still have the connected dominating set, okay? So you still have the connected dominating set, but it might not be latency S anymore. It might be latency S plus 1. Here, for example, it was latency 2, but after failure of this node 7, now it is a latency 3 CDS. But in some cases, if a vertex fails, you can see that it is not connected, it is not even connected dominating set. And so with this, we define the R robust latency SCDS. We say that this set D of vertices is R robust latency SCDS for graph G. If you consider any subset of D with size less than R, the vertex subset D minus F is still latency SCDS for graph G. And this is actually a generalization of our previous formulation when the right-hand side increases to R. Okay, instead of 1, we have R, but we still have the length as vertex cut condition here for our cuts. And then the remark here is that even integer separation is hard when S is at least 5 and R is part of the input, input of the problem. So, and then if you want to talk about cost of robustness for R equal to 2, you can see that this is the total time that's spent for solving the case R equal to 2. And this is the difference you can see between the objectives when R is 1 and R is 2. So in some cases, most of cases, for example, in this case, V70, which is an artificial like graphs, the difference is like a lot here. But in some cases, it is not. For example, we have a difference of 2. And then IEEE instances are infeasible because they contain articulation vertex. Okay, so if it contains articulation vertex, then it means that there is a vertex cut whose size is 1. So the left-hand side is at most 1, the right-hand side is 2, infeasible. So the problem is infeasible when the size of C, there exists as vertex cut or lengthless vertex cut C such that the size of C is less than 1. Okay, so this is what happens here for the IEEE instances with articulation vertex. So finally, we actually talk about the latency as CDS when delays are node weighted. So we actually define some weights based on closeness centrality. The more central, it's like the less delay they have. And then you see that the delays that we defined here are not symmetric actually. So if you want to send a message from 1 to 3, the delay, the node weighted delay is D1 plus D2. But if you want to send the message from 3 to 1, then it is D3 plus D2, which is different from each other. So I know the time is over. So, and then here are some results for the for some of our instances for the node weighted variant. So you can see that here the graph is weighted. That is why these S parameters are like large numbers that you can see here. But still, they are solved in 1 minute for some of our instances. Okay, so here are my references. I know the time is over, sorry about that. So, but please feel free to ask questions. And thank you so much for letting me to talk in this great workshop.